So now we're going to let ourselves fantasize a little bit. We've seen that we have solutions to y prime double prime equals, to be very specific, negative y. But they looked totally different at first from the exponential solutions. But then we started getting hints that they might have some connection, especially when we drew them in the plane, both solutions together as the x and y coordinates. And another thing to note is that this is flat out more important. It's more related. It's closer. It's actually a special case of our real main problem of oscillation. And in some ways, the solutions are better behaved, like they're bounded, for example. And when we did it in 2D, we got a circle instead of a hyperbola, which is a simpler shape. You learn it a lot simpler, a lot earlier. You learn circles a lot earlier than hyperbolas. So it's telling us we really want to put a lot of effort into understanding this as well as possible. And let's go ahead and with the fantasy. What if this could somehow be solved by e to the alpha t? That would unify things. That was the core of the solution to the other cases. Okay, except lambda equals 0 if you happen to do that one, but that really is a special case. So what would have to be true about alpha? Well, let's just fly. Let's just run with it. Okay. So this is this great part of mathematics where you get to just play with it. You get to try and see what happens, and don't say, "Oh, the rules say I can't do this." Okay. But just as a general aside, it's really important that I didn't start doing this right at the start until I was really, really motivated to. Until there seemed to be some reason that this might actually make sense. I didn't just start making stuff up. And of course, at some point you have to do a reality check. Does this really, really make sense? And I'll talk about that in a second. Okay, so here's what we would get. And this should be negative e to the alpha t. And of course, that's why we didn't do this before. It seemed like this was just a dead end. What? A number whose square is -1? Okay. Well, now we're going to be bold. In a minute, we're going to be bold enough to actually work with that. Okay. But let's see. Let's look at what we need. Okay. We're looking at alpha is the square root of -1 is another way to say it. Well, for positive numbers, you always get 2 square roots. And in fact, if this algebra that we're about to invent looks anything like ordinary algebra, putting a negative sign shouldn't matter because a negative sign should still square away. Okay, so we should get 2 roots. We should get 2 solutions, e to the alpha t and e to the minus alpha t. If we pick alpha to be one of these square roots, for example. Oh, hey, that's still exactly what we need. That's a good thing because it's a second order differential equation. We're supposed to have, we turn this into c1 e to the alpha t plus c2 e to the minus alpha t. We have 2 constants. That's enough to solve for the 2 initial conditions that we expect to need here. Okay, so that's a good thing. So we're still being pretty cavalier about whether this exists, but it's a good thing. Okay, and if we just get a little bit more complicated, instead of just -1, let's go back to the general negative lambda. We look at y double prime equals lambda y, and lambda is some arbitrary negative number. Okay, then we're just going to get, and it's like another good place to pause, if we want this kind of solution, what do we need to be true about alpha? We need that alpha squared, when that comes down twice, it has to match the lambda. And that's a negative number, and again, that's why we thought this was hopeless before. But we're going to be really bold and try to invent such an alpha. Okay, so remember, the goal was not to get just any solution here. We have solutions. We know that this should relate to cosine. Now let's see. Alpha squared equals lambda, so alpha equals root lambda. Okay, so this should have something to do with cosine. Well, cosine, that was root minus lambda t, and sine root minus lambda t. So somehow e to this mystery weird new number alpha t should correspond to cosines and sines of something of a related number, the square root of minus lambda, not the square root of lambda, this seemingly impossible guy. Okay, so that's an absolute requirement that if we develop this theory where this algebra makes sense, and then we can put it into this calculus, this function here, that it better reproduce this in the end. Okay, so that's going to be an important thing. And of course, there's another big hint. I'm getting to part D on the PDF at this point, what shape in the plane should these guys relate to? Okay, somehow e to the alpha t, when alpha is this bizarre new kind of number, the square root of a negative number, should have to do with circles. Oops, you can't see the circle. Okay, well, how the heck's that going to happen? Wait a minute, I thought e to the t looked like that. Okay, and that's going to be a beautiful part of the story. But it's definitely going to be a good check to see we're on the right track. Okay, now, finally, it's still going to be a tease, but because we haven't developed this theory of these weird kind of new numbers, which we'll call complex numbers, of course, um, let's write down what we really want to solve, not just the special case. If we put in friction and a mass and everything like that, oh, no prime there. Okay. If we put in the damping constant, that's what we really want to solve. Well, you know what? While we're fantasizing, what if our one size fits all purpose function solves that as well? Huh, okay, well, let's try it. It's the power of guessing is not to be underestimated. That's an alpha, doesn't look like it. Okay, so that's the components of this guy. Okay, so we would need m, we're going to just plug them in, m alpha squared e to the alpha t plus c alpha e to the alpha t plus k, just straight up e to the alpha t equals 0. This should be identically 0, the 0 function. Okay, so no matter what value e to the alpha t has, this should die. So I can just divide that out. It's the only way that's going to be true is if the coefficient, this common coefficient in front of e to the alpha t, is equal to 0. And so what I've got to be able to do is solve this equation. Not a totally arbitrary quadratic because the coefficients are all positive, but basically it's saying that if I can't, with this algebra, solve arbitrary quadratics, I'm probably going to be stuck. Okay. Notice how that relates to the very, very first video, the very start, where I said kind of the fake version of why you'd introduce complex numbers is to solve arbitrary quadratics. Well, here we have a better motivation for solving that because we're going to take that alpha and we're not just going to let it sit and say, ooh, it's something with eyes in it, whatever. We're going to put it right in here, although we don't know quite how to do that yet, and it's going to give us a solution, and it's going to relate to things like cosine and sine. And there's a certain amount of work involved there, but that's where we're going to go. Okay, so we'll start on the part 2 PDF in the next video.